All right, hi everybody. So today I want to make the case for explicit abstractions in robot planning. And I'll start by thanking my collaborators whose work I'll be talking about today. So I'm starting a new lab, and of course the most important thing that you do when you start a new lab is you make a logo for your lab. So I went to ChatGPT and I asked it to make me a logo, and it came back with this very nice logo, which I liked quite a bit. But I wanted to incorporate some Princeton colors, so I said, make the house in the background orange and don't change anything else. And then it made the house orange, but it also made the robot orange and the phone and the cups. And so I said, you made a bunch of stuff orange. I only wanted you to change the house. So then it made another edit. And this time, it kind of understood what I wanted, but it's kind of getting farther and farther away from the original logo, which I quite liked. So then I went to a human designer that I found online. I gave them the same sort of prompt, and we had a conversation about it. And they came back with not just an image, but also with this Adobe Illustrator source file, which I could open up and I could easily edit different parts of it. I could change the color of the font, or I could make things larger or smaller. I'm sure if I actually knew how to use Adobe Illustrator, I could do quite a bit of things. So I can edit it. I can also inspect this file. I can see that there's this sort of hierarchical structure to it. It has these layers which correspond to different parts of the logo. It's very intuitive. And I could also reuse different parts of this logo. So because I have this source file, I could, for example, easily take off the head, and if for some reason in the future I want to do something with horse robotics, then I can put the head of my logo onto a horse. So this Adobe Illustrator file is one example of an explicit abstraction. It's editable, it's inspectable, and it's reusable. And as the user or consumer of this kind of output, these are the properties that I think are really important to have. So looking ahead and imagining a future where we have robots in our homes, and we have these general purpose robots that can make dinner, serve it, clean up afterwards, help us into bed, and so on. I don't want to have just some kind of inscrutable black box planner where I give it a request, maybe in natural language, and it takes its sensors and outputs torques. This kind of black box would not be editable, nor inspectable, nor reusable. And I could certainly imagine cases where I have to go back and forth to kind of try to get the robot to do what I want, and it could be quite frustrating. So am I starting to make a case against using foundation models for robot planning? Well, no. I think we absolutely should take advantage of foundation models. They're very, very powerful tools. But we should do so in the context of a broader framework where we're also leveraging explicit abstractions. And so what I want to talk about in the rest of the talk is a couple examples from our recent work where we combine the power of foundation models and explicit abstractions. And I'll start with this work, Feast, which is going to be presented at the main conference and is also a finalist for the Outstanding Paper and Outstanding Systems Paper Awards. So Feast is a project led by Rajat and in the lab of Tapo Bhattacharjee. And this is the culmination of several years of work towards a mealtime assistance system that can feed someone in their home in the wild. So this, we can assist with feeding a plate of food and also assist with drinking and mouth wiping. There's a lot of different components to this paper. So we did a formative study with 21 care recipients. We have a lot of different systems contributions. And we also did a 5-day in-home study with 2 different care recipients. I'm not going to have time to talk about all these things. You should check it out at the main conference. But what I want to focus on in this talk are just the explicit abstractions that are running behind the scenes and making this possible. So nothing fancy here. We just have a couple of classic explicit abstractions. We have PDDL operators for sequencing together high-level skills. The skills themselves are implemented as parameterized behavior trees. For example, on the right, we have this acquire bite parameterized behavior tree for getting a bite of food. It has parameters like speed and the depth that the robot should dip a food item into a sauce, among other parameters. And we also have these programmatic head gesture detectors, and I'll talk about those more in a second. But because we have these explicit abstractions, what that enables us to do is have users actually make edits to the robot's behavior in the wild. So for example, if the user says, you're feeding me too slowly, we can take that natural language edit request, and we can look at the explicit representation of our skill, maybe acquiring a bite of food, and using some kind of language model, we can take the request that they made, look at the explicit abstractions, and directly update the parameters. We can also respond to inspection requests. So if the user asks, how long are you currently waiting between bites? Then we can take that question. We can again look at the explicit representation of the skill, and we can respond with an answer using a language model which might be 5 seconds. And finally, feast abstractions are reusable. So one example of this is that we enable users to create new head gestures that they can use to control the robot in the wild. So for example, this user wanted to create a new head gesture that was referring to slowly nodding his head. So he gives a natural language description of this gesture, as well as a couple of positive and negative examples of the gesture. And from that, we use, again, a language model to synthesize another kind of explicit abstraction, which is now a piece of Python code, which we can use on top of a head tracking module to actually detect this new gesture, which he sort of taught to the robot. Once we have this explicit abstraction, it can be reused. So for example, the same gesture could be used to indicate to the robot that the user is ready for another bite of food or for another drink. Another cool thing that we observed in our 5-day in-home study was that by enabling users to do these edits and inspections, they become better and better at personalizing the system to meet their needs. So for example, one of the requests that the user made early on was, he said, use button when completing a transfer when taking a sip. We have many different ways that the user can indicate that they're ready for a sip or a bite of food. And so he wanted to use a button when he was watching TV to avoid any noises happening, for example. So in response to this edit request, there was this sort of inspection result, which said the robot-assisted feeding system has been updated to use a button to complete actions when transferring drinks, utensils, and wipes. So the language model was kind of confused about what he intended. It not only updated the behavior of the system for drinks, but also for utensils and wipes. So the user was able to see this through the inspection. And then he had a bit of a conversation with the system. He asked, what other ways can I end a transfer besides pushing the button? And there was some more back and forth. And eventually, he was able to formulate this much more specific edit request that involved not just updating the drink, but also the utensils and the mouth wiping. And that was the correct update. So the takeaway from this last example is that by enabling users to do this kind of editing and inspection in the wild, we're enabling them to become sort of prompt engineers, where they're figuring out, how can I work with this robot to get it to meet my unique needs and preferences? So taking a step back and thinking about what kind of personalization we were doing in this project. We're doing personalization, but it's sort of analogous to how we have, settings on our laptops and phones, which you can sort of toggle and customize to meet your preferences. And from a design perspective, these sort of settings are great because it's very safe. We can fully anticipate what are all the different settings that a user might do in the wild. It's also very transparent to the user, so they can open up the settings and see what the state of the system is at any given time. But it's arguably not very flexible. We're not really enabling the user to fully personalize the robot in any way that they might want. And there's also not really a sense in which the robot is truly learning about the person or learning about its environment over time. It's more that the user has to directly indicate to the robot what they want at any given time. So this motivated our next project, which we call Coloring Between the Lines. And to start, we took a step back and we said, okay, what's the most flexible possible personalization that we can imagine? Well, we can start with a robot and we can just say, okay, consider the space of all possible plans that the robot could physically execute. Now, of course, we don't want to let the robot just do anything in the wild. We don't want it to break things and cause harm. So we need to introduce some universal constraints that enforce safety, like don't collide with stuff that you're not supposed to, and task knowledge, like maybe you tell the robot through constraints that if it wants to pick something, here's how it should do that. If it wants to move, here's how it should do that. So these are all sort of universal constraints that should apply to every robot working in every environment. But once we have that, we're left with this sort of null space of plans that satisfy these universal constraints, but are not yet personalized in any way to users. So then we go off and we start having the robot work with a particular user. And when we do, one mechanism for personalizing the robot is that we can think about introducing additional personal constraints that will be updated over time as the user continues to work with the robot to meet this user's unique needs and preferences. So as we have different robots working with different people, they start out with the same universal constraints, but gradually they learn to update these personal constraints to better fit the particular user that they're working with. So bringing this back to an assisted feeding example, maybe some of the universal constraints that we have in assisted feeding are the fact that the robot should never come into collision with something it's not supposed to. It needs to make sure that this plate of food is always going to be in reach and that it's able to actually prepare a bite of food. But then there's things that will differ between users. So for example, different users may be more or less sensitive to the robot occluding their line of sight when they're watching TV or talking to a friend. Users might also have different preferences about what dips they like. So for example, some people like ketchup or some people like barbecue sauce when they're eating tater tots. And there might be also differences in how the user wants to control the robot and tell it that it's ready for another bite of food. So maybe they want to use a button, maybe they want to speak. There's many, many possibilities there. So once we have these constraints, we have these universal constraints that apply to everyone, and we have these personal constraints that we're going to learn for each user, we're left with this space of plans that sort of satisfy both. And we can do some kind of constraint satisfaction solving where there's many different options here, and we take inspiration from task and motion planning when we're doing this to try to find a plan that satisfies all these constraints. So in the case of assisted feeding, what we saw in this project was that after the robot works with a particular user for 4 meals and learns about their preferences for dipping and their sensitivity to occlusion and their preference about how they want to control the robot, then the robot's able to plan to satisfy all the constraints. So first, it's going to move that plate out of the way to avoid a possible occlusion later on. Now it's going to prepare a bite of food, which it will choose ketchup because it learned that this user likes ketchup, and it'll wait for them to press the button because that's how the user wanted to control the robot, and it's satisfying all the constraints at the same time. Now we want to do this not just for a single task, but thinking about how we can do this over multiple tasks over very long-term deployments. And to that end, I think it's important that we don't think about just one monolithic constraint satisfaction problem, but we instead think about generating constraint satisfaction problems on the fly. So for example, when a user requests a bite of food, we might generate one constraint satisfaction problem. But later, if they request a drink, we'll generate a different constraint satisfaction problem, which might have some constraints in common. For example, the user's occlusion preferences might be in common between getting a bite of food and drinking. But these will be different constraint satisfaction problems that are generated, solved, and then the process repeats. So bringing this back to the assisted feeding, if we introduce a drink now, which this user's never told us anything about their preferences for drinking specifically, we see that the robot is able to reuse its learned preferences about occlusion and recognize that first it needs to move the plate out of the way to make room for the drink. Then it moves the drink out of the user's line of sight. And now when it performs assisted drinking, it's not going to be blocking the user's view of the TV. So how are we using foundation models in this project? Well, we use it in a couple of different ways. We use language models specifically. And we thought about constraints that can be parameterized by natural language. So for example, a user's preferences about what dipping sauces they like can be summarized in a natural language string, which is then a parameter to a constraint. And the constraint can be checked with, again, a language model. So we're grounding the language model in we're grounding the constraint using a language model. Another thing that I think is potentially very exciting, which we haven't done yet, but I think we can do in future work, is thinking about using language models to totally synthesize new constraints, which might be, Python code that further constrains and further flexibly navigates that null space. So the key takeaway from this project is that when we're thinking about how we can use foundation models to do this kind of in-the-wild personalization, where we're really having robots that truly are adapting to real users' preferences in the wild, we should do so by thinking about this null space, where we start out with these universal constraints, which apply to everyone and guarantee safety and task competency, but then we're left with this space of plans which we can further personalize. So this project was an example, again, of learning to personalize in the wild. But the kind of personalization that we're doing is somewhat like as you hang out with friends over a long period of time or work with collaborators, you learn about their preferences and what makes them unique. So people who work with me learn that I like to go to bed early. I learned from working with Rajat that he really hates barbecue sauce, but he likes ketchup. And Tapo prefers comfortable footwear. So these are things that you learn through working with someone over time. But in the final projects I want to talk about today, I'm going to consider a different sort of in-the-wild learning, which is more analogous to having a robot that can learn totally new concepts in the wild. So something more like somebody teaching me how to use Adobe Illustrator. So bringing this back to an example where we have a robot that's preparing meals and serving it. Maybe one day I have a robot in my home, and I bring home a new juice machine, and I want to teach the robot how to use it. So maybe I give the robot a couple of egocentric demonstrations for how to use it. And this is a project, by the way, led by Nishant and Ashay. So this is Nishant giving egocentric demonstration of using this new juice machine. It involves putting that fruit into the top and turning the dial to turn the machine on. And then we get juice. So in this project, which we call Picks to Pred, we're interested in the question of how can we start with a couple of demonstrations like the one that I showed there, and also some skills that we have beforehand, like picking and placing and moving and pushing potentially. So we take those demonstrations, we take these parameterized skills, which the robot already has, and we want to learn abstract world models in particular form, which we can then use to do planning. And since we can plan, we can then generalize to tasks that involve new objects, new rooms, new goals, much longer horizons, and very different skill sequences than what was demonstrated to the robot. So the key question in this project was, how can we invent these predicates, these symbolic relations that the robot will include in its abstract world model for planning? And we wanted to see if we could use VLMs because of how well they can generalize to differences in vision, and we were able to just ground right in images. So our first idea was, okay, let's take a VLM and let's just ask it to directly look at the demonstrations and propose predicates that we can use for abstract world models and then for planning. The problem with just directly asking VLM to do this is that the VLM doesn't know how we're actually going to use these predicates. It's not aware of the fact that we're going to take these predicates, we're going to learn an abstract world model, and then we're going to plan with that world model. So the VLM is not really planner aware. It's not aware of our real objective, which is ultimately efficient and effective planning. So then what we thought was, okay, let's take the output of the VLM, and let's not just directly use those outputs, but instead think of the VLM as proposing candidates, a large pool of candidates, from which we can then select by directly optimizing for the thing that we care about, which again is fast planning. So we take these candidate predicates, and we run an optimizer, which in this case was just a simple hill climbing algorithm, to select a final subset of predicates that are explicitly aware of our planner. So once we do this, and we use those predicates to learn an abstract world model and use it for planning, we can transfer to a robot, for example, a spot robot, and we can ask the spot to make us some juice, which we can go ahead and do. It also uses planning to recognize that the cup is not yet in position like it was in the demonstration that I showed before, so it's going to have to pick and place that cup to make sure that it's there. You also wouldn't want the robot to turn on the juice machine before the cup is there, right? So it's good that it realizes that's sort of something it needs to do first. And then it turns the dial, and we get juice. And again, we get this nice generalization by virtue of the fact that we're planning, and we have these abstract world models, and we're using VLMs, which are able to generalize to new rooms with new lighting conditions and so on. So this is a room that the robot has never seen before. There's no demonstrations in it, but we just brought the robot and brought the juice machine to a new room, and it was able to make juice, this time actually using a pear in this new room. So the high-level sort of technical takeaway I want to drive home in this project is the fact that maybe VLMs and foundation models in general are not aware of the fact that we're going to use them for efficient and effective planning, but we can still use them as a prior on top of which we can do optimization to sort of ground them back into our real objective, which for us is learning to plan quickly. And zooming way back out, if our goal is ultimately to empower users with robots, I think it's essential that we really ask ourselves, how can we let users edit, inspect, and reuse what the robot is doing, these abstractions? And I think the best way to do that is to combine the strengths of both foundation models and explicit abstractions. Thanks very much.
All right, thanks so much, Tom, for showing us how to use abstraction as foundation model for robot planning. We'll take 2 questions.
How do you think about what level of abstraction you want to target? Like users are different, but also the abstractions provided are very different as well. Like in your Adobe file, for example, I don't know the internal file format. Maybe it's XML. You could go in and edit XML directly or something, and that is an abstraction that you could work at. Or you could work at the interface that Adobe Illustrator itself provides or things like that. So how do you actually navigate those options in terms of where the right abstraction level is for each part of the system?
Yeah, that's a great question. Thank you very much. So as you alluded to, I think there's no one right answer to the question of what the right level of abstraction is. I think ideally we would have many levels of abstraction all kind of building on each other. It might look like a hierarchy. And so in some of the work that I presented here, we have two levels, which is a start. So for example, we have sort of an object-centric abstraction where we know that there are these objects and they have features. And then we have this symbolic abstraction, which builds on top of that. But that's only a start. I think we want to have a rich repertoire of many different kinds of abstraction that are all grounded in one another. And we can enable a user to sort of interface with the system however they want. So some users might prefer to sort of give very high-level inputs or edits to the system, and higher-level abstractions would be great for that. Others might really want to get into the details of how it's working, and lower-level abstractions might be better for that. So yeah, I think we want to have as many abstractions as possible at different levels to give users flexibility.
Hi, thanks for the nice talk. I have a question about predicate generation thing, which you talked some time back. So you told that VLM proposed the list of predicate and then you run the optimization. So it will not be faster if you connect the VLM with the retrieval augmented generation based on the model of the environment to select what is the best possible predicate in that particular scenario. What do you think about that?
That's a great question. So I'm not sure that retrieval augmented generation would help in these scenarios because it's not as though we have examples of what predicates were used previously that we could look to sort of retrieve from that knowledge. We have these candidates which are proposed by a VLM, but we still don't know for any particular, even for a demonstration, which were the predicates that were most relevant for that demonstration. So I'm not sure that RAG would give us too much leverage. Another thing that is maybe important to note is for many predicates, they're sort of synonymous. You can describe the same concept in different ways, but it turns out that certain synonyms are going to be better for planning than others, for example, because maybe the VLM more robustly identifies certain words. And that's something that really is not evident just from looking at the data itself. You really do need to ground in the objective of fast planning to make that possible.